Hi guys, welcome to Momentum with Vedantu. Hi Surinder. Surinder is here. Smartbook is here. Fab Phoenix is here. Superb guys. Superb, superb, superb. Welcome to Momentum with Vedantu guys. And today is the start of thermodynamics. We are going to do thermodynamic variables and the basics of thermodynamics. Okay. Hi Hina. Hina is also here. Superb, superb, superb. So glad you guys are here. Okay. My regular crowd. I love you guys. I love you guys. Superb, superb, superb. Okay, Mahita is also here. Coffee Coffee is also here. Smart book, I'm doing good. I'm doing good. I have changed the timings to 4 to 5 on your suggestions, guys. You guys wanted me to do that. Okay, and the advanced classes, guys, are going to go on for just few more days. After which we will switch back to a regular one class for 11th, one class for 12th, one class for 11th, one class for 12th. No revision classes for a long period, okay, until we at least finish the syllabus. So that is the plan. That is the plan. Okay, Kavya has a request. Kavya, what is your request? Tell me. Kavya has a request. Kavya. Afra Baiju is also here. Hi Hina. Okay. Sir, do some questions in live class. Balram, I will do that. I will do that. Okay, I will do some. We will do some questions in the live class. So, guys, welcome to Momentum with Vedantu. If you don't know who I am, I'm your master teacher Aditya Pandya. I'm going to teach you physics, and today we are going to study thermodynamics. Thermodynamics is the last part of thermal physics that we will study, and it has the most important applications as far as future is concerned. In the future, you will study a lot of thermodynamics, especially if you take up mechanical engineering or if you take up aeronautical engineering. Okay, it's very very important. Okay, I myself have done mechanical engineering, so I have to study this topic a lot. Okay, after finish 12, will you revise 11? Yes, I will. Okay, thank you so much, Balram. Thank you so much. Entertainment 2015 is also here. Super guys. Let's start today's class. Okay, if you haven't liked, shared, or subscribed to our channel, please do that. Also, at the same time, let's talk about our Hall of Fame. Okay, the first person to give the correct answer is da 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 da. Surinder Singh. Okay, Surinder Singh gave the first correct answer. The gamma is 1.44 diatomic gas. But other than that, so many of you gave the correct answer. Godavarthi also gave the correct answer. Smartbook also gave the correct answer. Entertainment 2015 also gave the correct answer. And Dhanush B gave almost the correct answer. I would consider it correct. I don't know Dhanush how Dhanush B got to 1.38, but let's say it's very close to 1.4. So I just consider it as a correct answer. Okay, all right. Smartbook has given all the answers. Superb, superb. Smartbook, I know. I always see your comments, Smartbook. I always see your comments. Also, at the same time, guys, I suggest you join our Telegram group if you want notes. And also, at the same time, if you have any doubts, you can directly message me on Telegram at this address. Okay, this is my address on Telegram. You can just directly message me on doubts. I can solve it. Try to solve it. Okay, I have solved doubts in the past. I will solve it in the future as well. Don't worry. Okay. Yeah. Very good. Very good. Very good. Okay. Chalo guys, so let's start today's lecture now. Let's start today's lecture. Today we are going to start with thermodynamics. Today is supposed to be the basic lecture, so we are mostly going to talk about thermodynamic systems and variables. Okay, let's just understand what this chapter is about, guys. It's just such a khatanak chapter. So let's just understand what it is about. Okay, so thermodynamics is made up of two words, thermo and dynamics. Okay, so basically we are going to talk about the heat in flow and what it can do. Flow of heat from one system to another system and what it can do. Okay, I think there is some problem here. I think there is some problem here. These slides, this slide at least, the last slide was okay. This slide is shifted towards the left. Why is that? Why is that? Is there a diagram here? Tell me if there is a diagram here. No. Oh, this is just so big. Okay, let's take it you as well. Yeah, very good, very good. Now it's okay. Now it's okay. I'm sorry for that, guys. Okay, minor issues. Anyways, so heat and thermodynamics, we are going to talk about. Yeah, Afra Baiju. Yeah, by the way, this chapter, after this chapter is over, we'll do a poll on which chapter you want me to do next. Okay, based on that, we'll just start the next chapter. So, thermodynamics is basically study of thermo and dynamics, heat in flow, and how heat can be converted to various different things. Heat can be converted into internal energy. Heat can be converted into work, how to do that, how that happens, all those things we will talk about in this chapter. Okay, now first thing before we start this chapter, guys, you need to know that work and heat are interconvertible. Work and heat are interconvertible. Okay, you can convert work into heat and you can convert heat into work. One of those is easier than the other. Okay, this one which is shown here, which is conversion of work to heat, is easier. Okay, it's easier. Why is it easier? That you will understand by the end of this chapter. Okay, so but just for now, just believe me, this is easier. If you see in this situation what this lady is doing, is using friction to convert work into heat. Okay, that is what is happening. Also, at the same time, if you have ever been in a car or any vehicle of any kind, all those things have something called an engine. Okay, and the main function of that engine is to convert heat into work, to convert heat into work. But as I said, this is a little bit hard. Now I'll tell you what is the problem here. Here, no matter however much work you do, you always can you can always get equal amount of heat. Okay, the amount of heat generated will be same as the amount of work done. But here, what happens is, in case of an engine, there is always some heat which is wasted. There is always some heat which is wasted. If you give some heat, only part of it gets converted into work, the other part gets wasted. Okay, now why that happens, once again, you will have to understand by the end of this chapter. Right now, you will not be able to understand. Okay, but basically, in case of cyclic process, this has to happen. There is no other way about it. Okay. Alright guys, now let's talk about basic terminology that we will use in this chapter. Okay, at the end of this chapter, we need to understand how a basic engine works. Okay, at the end of this chapter, we will talk about an ideal engine called a Carnot engine, and we need to understand how that engine works. But before we get to that, we need to understand what the variables are, how they react with each other, how they interact with each other, and all those things. So first of all, let's just define. Okay, like when we study Newton's laws of motion, we always keep talking about bodies, particles. Now you never need to understand what those are because you have seen those particles. You understand what I mean by body, you understand what I mean by particle. But in thermodynamics, we need to be more specific in talking about our terms. When I say a system, what do I mean by a system? When I say surroundings, what do I mean by surroundings? Okay, basically, let's talk about basic terminology in thermodynamics. In thermodynamics, we always study something called a system. Now, this system can be anything. This system can be a pan, this can be a balloon, it can be a cup of tea or anything. Okay, the system can be anything, but we always talk about a system. And for most part of this system, for most part of this chapter, inside this system, we will mostly have ideal gas. Okay, it's not necessary that it should have ideal gas, but for most part of this chapter, this system will always be filled with ideal gas. Why do we study ideal gas here? Because guys, it's just easier to study ideal gas. Okay, so for most part of this chapter, our system will be filled with ideal gas, and then there will be a boundary to this system, and outside the system there will be surroundings. Outside the system there will be surroundings. Okay, together the system and the surrounding make up the universe. Together the system and the surrounding make up the universe. I hope everybody is following me so far. Okay, Surender, Anu, Afra, do you guys understand? Do you guys understand? Give me a thumbs up if you understand. Give me a thumbs up when you start understand. Okay, yeah, Are Dhanush, no issues, no issues. Okay, I'm just starting with the basic terminologies, Dhanush. You will understand very soon, very soon. Okay, no issues. Hi, Sakshi. Okay, so now let's first talk about boundaries. What are the different types of boundaries and what they can do? Okay, so we can have various different types of boundaries. We can have a fixed boundary versus a movable boundary. Okay, basically, what is a fixed boundary and a movable boundary? Here, the shape of this container is fixed. Okay, here the shape of this container is fixed, and that means if I heat this container, the volume of the gas inside remains the same. Okay, such boundaries are called fixed boundaries. Here, if you see, this balloon can expand, can compress. Such boundaries are called movable boundaries. boundaries. Okay. Also at the same time, we can divide boundaries into real and imaginary. Okay. In this case, if I want to talk about water in the container, then I will make assume an imaginary boundary here, and I will consider water which is inside that boundary as my system. I will consider water which is inside that imaginary boundary, imaginary horizontal plane as my system. Okay, so boundary doesn't always need to be real. They can always be also be imaginary boundary like this. This will be my imaginary boundary in this case. Okay, I hope everybody understood. Now, based on this, we can divide our thermodynamic systems into three categories. Okay, based on this, we can divide all of our thermodynamic systems into three categories: open system, closed system, and isolated system. In this chapter, guys, we are mostly going to study these two systems. We will not study this system, okay, because it's a little bit more complicated, but we are mostly going to study closed and open system, closed and isolated system. First of all, what is an open system? Open system is a system where there is a matter exchange with the surroundings. There is a matter exchange with the surroundings, and there is a heat exchange with the surroundings. Okay, both heat and matter can come out or go inside the system. Both heat and matter can come out or go inside the system. For a closed system, there is only heat exchange with the surroundings, and for an isolated system there is no type of exchange. Okay, if I have to give you real world examples, because whatever I wrote it's very confusing, so let me give you real world examples. Okay, if I have a cup of tea here, guys, if I have a cup of tea here, then this is an open system. Why is it an open system? Because here water vapor can go out of the system, matter can go out of the system, and heat can also go out of the system. Such a system is called an open system. Okay, and a cooker, this is a cooker. Let's assume that there is no CT here. Okay, or assume there's a CT. Okay, but this cooker can be considered as a closed system. Okay, because here as long as the CT, the top part of the this, I don't know what you guys call it. Okay, as long as it doesn't go up and the water vapor doesn't go out of that of the cooker, I can say that this is a closed system. Only heat can go in and out of this system. No matter is coming out. Okay, only heat can go in and out of the system. No matter is going out. Such a system is called a closed system. Okay, and what is an isolated system? A thermos flask is an isolated system. Here, neither heat, no, vessel. You call it vessel. Okay, I call it CT. You call it vessel. Yeah. Okay, the bottle is cello. Okay, we only use proper branded bottles on our lectures here. Okay, no faltu bottles. No, only cello. Okay, huh. So, so this is an isolated system. There is no exchange of heat or matter with the surroundings. Okay. Now, guys, I'll give you an example. Tell me what type of a system is it. Okay. Everybody should tell me in the chat. Okay. Everybody. It's a very hard question. I know it's a very hard question, but you can do it. I believe in you guys, all 15 of you. Okay. Tell me which type of system is it. Everybody, I want to see 15 answers. I want to see 15 answers. Everybody can tell me which type of system is this. I know you guys know. I know you guys know. Yeah. It's a hard question. I understand. You can tell me. Yeah, smart books, Oxy Entertainment, Dhanush, everybody's correct. It's an open system. Okay, it's an. Hmm. Yes, Surendra Siddharth, Balram Fab Phoenix, Rajani, all of you are correct. This is an open system. Here, both matter and heat are being exchanged. Okay, so I hope everybody understands the difference. Okay, now that we know what the thermodynamic system is, let's talk about how do we measure that system. Okay, how do we measure that system? Now, in general, when we are talking about a Newton's laws of motion, okay, I'll keep giving examples of Newton's laws of motion, because Newton's laws of motion is very you can draw parallels. Okay, so in this case, if we are talking about a block, what do we define a block with? We always give it some properties. Okay, we always give this block a certain position, we always give this block a certain velocity or acceleration or whatever. These These are called properties of that block. These are properties of that system. That block is defined, its future is defined by these values. Okay. Similarly, in thermodynamics, we have something called thermodynamic properties. Okay. And these thermodynamic properties, you have known always, these are temperature, pressure, mass, volume, and energy of a system. Temperature, pressure, mass, volume, and energy of a system. Okay, these properties tell us about a thermodynamic system. These properties tell us about the amount of energy content of a system, or how much work it is capable of doing, how much heat it is capable of absorbing. All those things can be told to us by these properties. So these are called thermodynamic properties, and these thermodynamic properties are divided into two different parts: intensive properties and extensive properties. Okay, now how to understand the difference between intensive and extensive properties? Let's say I have a chamber of gas. Okay, let's say I have a chamber of gas. Inside this gas, I have gas at pressure P, volume V, temperature T, and mass M, and number of moles N. Okay, now what I do is I put a partition in between. What I do is I put a partition in between. Now I have two different gases, two different chambers. Now of the one chamber, if you see, of the one chamber, the pressure will still be P because I have just put a partition in between. Okay, and the temperature will still be T, but for this left part of the system, the volume will be V by 2. Hi guys, hi. I'm sorry. My laptop restarted. I'm so sorry what happened. I have no idea what happened. Let me just restart everything properly, okay? I don't know what happened, but the laptop just went boof and it just restarted. There was a blue screen of death, okay? Have you guys seen the blue screen of death before? I guess you have must have seen the blue screen of death before. Have you? Have you seen? I have seen that. I have seen that. Okay, so I had that, and because after that screen, what happened is just everything just turned off. Okay, everything just turned off. No idea what happened. Okay, yeah, okay, chalo. Hi everyone. So let's start the lecture again. Okay, let's start the lecture again. Usha Nandini is asking if I am married. Well, I don't know. Okay, so in this case, guys, in this case, what do we do in this case? Intensive properties. Yeah, I was talking about intensive properties. Let's explain this again. Okay, fatafat se. If I have a container has gas, pressure P, volume V, temperature T, mass M, and number of moles N. If I add a partition in between, then for the container, the gas in the half of the container, here the pressure will still be V P, the temperature will still be T, but the volume will become V by 2, the mass will become M by 2, and the number of moles will become N by 2. Okay, these are what we call extensive properties. These depend on the quantity of the system. Okay, and the first two are called intensive properties, which are independent of the quantity of the system. Okay, these are independent of the quantity of the system. I hope everybody understood. Okay, yeah. I hope everybody understood. Okay. Yeah, I seriously don't know if I am. Okay, so I'm not joking. There, it's the truth. It's the truth. Okay. Yeah. Okay. Anyway, so yeah, I had a friend at IIT. Okay, and my friend at IIT, he always he actually did not know if he was married or not because he had memories of being married when he was young. Okay, and after he got married at that young age of, I don't know how old he was, he never saw his wife again, and now like at that when he was in IIT, he didn't even have an idea whether he's married or not. So I really had a friend who was in this condition. He did not know whether he was married or not. Okay, there are people like that out there. Okay, anyways, let's go back to this. Okay, yeah, child marriage is horrible, but it happened to him and it was Funny. Okay. Anyways, yeah. Let's talk about the approaches of how we will study this. Okay, let's talk about approaches. So, if you study Newton's laws of motion, guys, so if you study Newton's laws of motion, what you do is you talk about one body in Newton's laws of motion. Okay, you talk about the velocity of that body, acceleration of that body, force on that body. You talk about one body and you do analysis based on that. Okay, now if you do that to this system, if you want to apply those Newton's laws to this system is very, very complicated here. Why? The problem here is, guys, that there is not just one single body, there are billions and trillions of molecules here, and you can't study each of them individually. Okay, studying each of them individually would be calling a study would be study of single particles. When you go to in each and every individual particle and you apply Newton's laws on those particles, okay, that would be microscopic studies, and it's not possible. What we can do is we can do macroscopic studies. Basically, we just take all the particles at once and we study all of them at once. Okay, instead of defining velocity of each particle, we define things like most probable velocity or RMS velocity or average velocity. These three terms are applicable to all the particles together. Okay, this is macroscopic study of the system, where we are studying this particles not individually but statistically, all of them together. Okay, now that is the same thing we are going to do here when we talk about thermodynamic variables: the pressure, the temperature, the volume, the number of moles. These are macroscopic variables. We are talking about all the particles together. Okay, and that is the only way in which we can study thermodynamics. Okay, that is the only way in which we can study thermodynamics, because बहुत सारे particles. Okay, so now let's talk about state variables and path variables, guys. Okay, so what are state variables and path variables? So in thermodynamics, when I want to know the state of a system, there are three basic variables that I always need to know. Of a system, I always want to know the pressure, the volume, and the temperature. If I know this, I know where my system is at. I know if my engine is basically in the expanded form right now or in the compressed form right now. I have to know these three variables. So these are what we call, guys, state variables. They tell me where the system is at. They tell me where the system is at. You can think of them as thermodynamic coordinates. You can think of them as thermodynamic coordinates. Okay, just say in Newtonian mechanics we have XYZ coordinates. Here we have three coordinates: pressure, volume, and temperature. They tell us where the system is at right now. Okay, and let's say the system started at this position and it didn't like to be at this position and it went to another position, position 2. Okay, then the variables pressure, volume, and temperature at that point are the state variables of that state, are the state variables of that final state. This is the initial state variables. This is the final state variables. Okay, they tell us where the system was at and where it is now. Okay, the initial and the final state of the system. But whatever happens in between, those are called path variables. Okay, those are called path variables. Okay, whatever happens in between. So for example, when I took the system from 1 to 2, I might have given this system, I changed its pressure, I changed its volume, I changed its temperature. How do I do that in general? I generally do some work, or I generally give it some heat. Okay, those are the two basic things how I will do that. So when I did that, I might have given the system some heat, or I might have done some work on this system. These are what we call path variables. They come only into play when a system is transitioning from one state to another. When a system is transitioning from one state to another. I hope everybody understood. Okay, I hope everybody understood. Okay, everybody. Path variables that happen in transition, state variables, the initial and the final state of the system. Okay, I hope everybody understood. Okay, that's what they have also given here. Okay, and by the way, this entire thing is also called this line is also called a process. Okay, there are various different types of process. If you want to go from one to two, how many different options you have to go from one to two? Oh, you can go on this path, you can go on this path, you can go yeah, on this path, you can go on infinitely many paths. Okay, so how many different types of path you can take? Infinitely many different types of path you can take, and each path will be called a process. So to go from one to two, I can do that in how many different processes? By how many different processes? Infinitely many different processes. Okay, but some of those processes are going to be special, some of these paths are going to be special, and we are going to study them later. Okay, those are called standard processes. Okay, some of these paths which are special are called standard processes. We will study them a little bit later. We will study them a little bit later. Okay, I hope everybody understood. Infinite, exactly entertainment 2015. Infinite, infinite, infinite. Okay, these are states, and this is the path or the process. Path or the process. Okay, I hope everybody understood. Now, there are something called state functions and path functions. Okay, there are something called state functions and path functions. This you will understand a little bit later properly. Okay, right now you will not be able to understand, but if I had to tell you, if I had to define it to you, then in Newton's laws of motion I would define state functions as displacement. Do you guys know displacement? Do you guys know displacement? If a body goes from 1 to 2, it doesn't matter on which path it goes, A or B or C, its displacement will always be same. Such functions are called state functions. Okay, and in thermodynamics also we have some state functions. If a body goes from A to B to C, here the change in internal energy, the change in internal energy is going to be same for all the three processes. Okay, is going to be same for all the three processes. What am I saying? How am I saying? I will explain later. Okay, I will explain later, but for now these are basically the equivalent of displacement. It just depends, a change in internal energy just depends on where it was initially and where it was finally. It doesn't matter what happened in between. It started from 1, reached 2, then that is only what I require. In the in between it would have gone on whatever path. I don't care, guys, I don't care. The value of change in internal energy will always be same. It's a kind of like displacement. Such functions are called state functions. Okay, state functions. Oh my god, state functions. Right. Alright, then with state functions we also have something called path functions, guys. With state functions we also have something called path functions. यहाँ पर नहीं है क्या path functions? No, we don't have path functions here. Okay, let's just write path functions. Path functions. Okay, what exactly are path functions, guys? You can think of path functions as the equivalent of distance. Okay, you guys remember distance in Newtonian mechanics? You remember distance in Newtonian mechanics? What exactly happens if a particle goes from 1 to 2? If it goes along this path, distance will be different. If it goes along this path, distance will be different. Distance will be different along this path. It depends. Its value depends on the path which you take. Similarly, in thermodynamics, these two variables, the heat given to the system or the work done by the system, okay, heat and work, these are path functions. Their value depends on what path you take to go from initial to final state. Okay, this also I will explain a little bit later in some time. I will explain a little bit later in some time, not right now. Okay. I hope everybody understood, guys. I really hope everybody understood. Now, let's work our way towards zeroth law of thermodynamics. There's a lot of theory here today, guys, and I understand there's so much theory, but all these you just need to remember and understand, because otherwise it's like I am teaching you ABCD of thermodynamics. thermodynamics. Okay, it's like learning ABCD. There is not much fun in learning ABCD when you do it the first time. Okay, but it's just you have to get through it. Okay, once you know the ABCD, then you will start making words, then you will start making sentences and all those things. So boring today, I understand, but let's get through it. Okay, so let's talk about temperature and zeroth law of thermodynamics. Now, before talking about zeroth law of thermodynamics, guys, let's talk about two different types of walls that we can have in a system. Okay, now if you go back to our open, close, and isolated system, okay, where is the open, closed, and isolated system? This is an isolated system, and this is a closed system. Now, if you see, there is heat coming out and going in into the system, but there is no heat going able to go out or come out of the system or go into the system. Okay, such walls are called adiabatic walls. Such walls are called adiabatic walls. Adiabatic walls are basically walls which do not allow any transfer of heat, which do not allow any transfer of heat through them. Okay, and such walls here are called diathermic walls. Such walls are called diathermic walls. Diathermic walls are walls which have no issues from heat getting transferred. Okay, jitna heat, whatever heat you transfer, the diathermic wall will never stop. Okay, now in real life, no wall is perfectly diathermic and no wall is perfectly adiabatic. We have always a range in between the two. But when we are studying this chapter for the first time, we will always consider all walls as either perfectly diathermic or perfectly adiabatic. Okay, we will not consider a system which is a mixture of the two. Okay, so I hope everybody understands the difference between a diathermic wall and an adiabatic wall. If there is a temperature difference, the adiabatic wall will not let heat pass through it. But if there is a temperature difference, the diathermic wall will be like, ah, go, 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 man, go. Okay, that is the difference. Now, if you understand the difference between adiabatic wall and diathermic wall, guys, then let's talk about the second part, which is a thermal equilibrium. Now, guys, I think everybody knows that heat always travels from higher temperature to lower temperature. Heat always travels from higher temperature to lower temperature, and after a while, heat flow will stop when temperature is same for both the left and the right part. After a while, the heat flow will stop when temperature is same all around. Hi, Alia saying hi. Okay, so now how will you see how do you define thermal equilibrium? Okay, how do you define thermal equilibrium? So let's talk about this. Okay, and in order to understand thermal equilibrium, guys, you need to understand difference between two different types of equilibrium. Okay, one second. In order to understand that, you need to understand two different types of equilibrium: static and dynamic equilibrium. Static and dynamic equilibrium. Okay, now do you guys know the difference between a static and a dynamic equilibrium? What is a static and a dynamic equilibrium? Hi, Balram Singh. Yeah, Balram Singh knows the difference between a static and a dynamic equilibrium, guys, but I will still tell you the difference between this. Okay, let's say I'm balancing two bodies of mass, okay, on a fulcrum like this, and they are perfectly balanced. Okay, so I will say both the masses are in equilibrium. Such a thing is called a static equilibrium. Such a thing is called a static equilibrium. Okay, now what exactly is a dynamic equilibrium, guys? What exactly is a dynamic equilibrium? So let's say I had a container. Okay, let's say I have a container. Oh God, I am. Yeah. Okay, I have a container, and in this container I have filled some water. Okay, in this container I have filled some water, and also at the same time what happens is I make a hole here at the bottom. I make a hole here at the bottom. Okay, then if I make the hole near the bottom of the container, what happens, guys? The water starts leaking out. And when the water starts leaking out, the height of the water level will start decreasing. But I am like, no, I want this height level to be maintained. but also I am stubborn at the same time, so I am not going to close that hole. What I'm going to do is I'm going to start a tap. I'm going to start a tap here and keep adding water. I'm going to start a tap here and keep adding water. Now, when I do that, what happens is water is coming in, water is going out, and the height level stays maintained. Such an equilibrium is called a dynamic equilibrium. Such an equilibrium is called a dynamic equilibrium. Okay, I hope everybody understands. Now, in this case, if you see at macroscopic level, the height of the water level remains the same. So that is true. But at microscopic level, there is constant flow of water. At microscopic level, things are constantly changing. Such an equilibrium is called a dynamic equilibrium. Okay, now you have to understand that similarly, in case of thermodynamics, the equilibrium between two systems is also a dynamic equilibrium. What do I mean by this? Now, everybody knows that if I have a system, okay, like this, let's say I have a container, I have a wall in between. This wall is a diathermic wall. Okay, this wall is a diathermic wall. Here I have a gas at temperature 20 degrees Celsius. Here I have a gas at temperature 0 degrees Celsius. Everybody knows what is happening here. What is happening here? Here, heat will get transferred from where to where? From where to where? Heat will get transferred from here to here. Okay, heat will get transferred from here to here. I think everybody understands that. Heat travels from higher temperature to lower temperature. But what will happen? What will happen if the temperature of both of them, if temperature of both of them is 20 degrees Celsius? In that case, what will happen? So now what I will say is that they are in a thermodynamic equilibrium. They are in a thermodynamic equilibrium. And there is a reason why it's called a dynamic equilibrium, guys. Why is it called a dynamic equilibrium? Because when these have the same temperatures, when these have the same temperature, it's not as if no heat exchange is taking place. At microscopic level, heat exchange is still taking place. Okay, there is still transfer of heat from here to here, and also at the same time there is still transfer of heat from here to here. But what happens is that both heat transfers in both the directions have the same value, and therefore the temperatures will remain same. The heat transfer is still taking place. Okay, similarly here as well, guys, here as well, there is, I made this wrong diagram. Actually it's not like how it is happening. What happening is that there is a lot of heat going from here to here, and also at the same time, believe it or not, there is also a little amount of heat going from here to here. There's also a little amount of heat going from here to here. Okay, but the heat going from right to left from 0 to 20 is very small compared to the heat going from 20 to 0. So overall you can say overall net heat is going from 20 to 0. Okay, net heat is going from 20 to 0. I hope everybody understood. Okay, okay, okay. All right. Alright guys, I hope everybody understood. Now based on this, let's do a small question. Okay, everybody should be able to answer. Tell me the correct answer. If we use adiabatic walls in place of diatomic walls, then is it possible to achieve thermal equilibrium? Tell me. Simran, I am good. Simran, I'm good. Uman Sharma, thank you. Umansh wants to call Pluto a planet. Umansh, I don't know if you watch Rick and Morty. Okay, but don't do that. You might get into trouble. Okay, I'm good. Okay, very good. Yeah, tell me, if this is an adiabatic wall, then is it possible to achieve thermal equilibrium? The correct answer, guys, it's obvious here. I think it's obvious. Yes, it is obvious. It's obvious. Yeah, Omansh, you have the same bottle as me. Okay, what type of bottle is this? What closed, open, or isolated? Mm-mm-mm. Now, what type of bottle is this? Closed, open, or isolated? Okay. Hi, Dhanush. Yeah, this is. Thank you, Dhanush. Thank you, thank you, thank you. This will be. The answer here will be no because it's an adiabatic wall. There will not be any transfer of heat. Okay, there will not be any. Wow, green is so much not visible. There will not be any transfer of heat. Okay, and therefore equilibrium cannot be achieved. Equilibrium cannot be achieved. Okay. Now, guys, if you understand so far, then let's talk about zeroth law of thermodynamics. Okay, zeroth law of thermodynamics. Okay, now I used to call it a useless law of thermodynamics because you really don't understand anything from zeroth law, and it's just there to exist. Okay, but there's a purpose for zeroth law of thermodynamics. Okay, anyways, we'll get to that purpose in some time. But what exactly is the zeroth law of thermodynamics? What exactly is zeroth law of thermodynamics? Okay, but before understanding zeroth law of thermodynamics, guys, before understanding zeroth law of thermodynamics, let's talk about a small topic called internal energy. Okay, let's talk about a small topic called internal energy. Okay, I think everybody remembers internal energy. What exactly is internal energy? What exactly is internal energy? Internal energy is basically the energy stored by all the molecules. Energy stored by all the molecules. Okay, so if let's say I have two gases on either side. If I let's say have two gases on this either side. Okay, I have gas number one here and I have gas number two here. Okay, now tell me this. If this one has more internal energy, if this one has more internal energy and this one has less internal energy, okay, then if this wall is diathermic, where will heat flow? If this wall is diathermic, where will heat flow? Option A 1 to 2, okay, and option B 2 to 1. Where will heat flow? 1 to 2, 2 to 1. 1 to 2, 2 to 1. And option C can't say. Okay, option C can't say. Can you guys tell me the correct answer? Can you guys tell me the correct answer? Okay. Where will the energy flow? Where will the energy flow? Where will the energy flow? Okay, option A or B or C, guys. Option A or B or C. Hmm. See, the correct answer is, see, everybody thought of that only. Everybody thought of that only, that if this has more energy, then this has less energy. Okay, the energy is supposed to flow from one to two only. Okay, let me give you one more example. Okay, let me give you one more example. This is a very weird example, but I don't know if you guys are aware of something called GDP. Have you guys heard of something called GDP? What is GDP, guys? What is GDP? What is GDP? GDP is called gross domestic product. Okay, gross domestic product. Okay, it's basically the sum of all the, you can think of it as it measures the richness of a country. It measures the richness of a country. Okay, so basically yeah, GDP basically tells you how much a country is producing, how much a country is earning. Okay, so guys, if I talk about India's GDP, okay, if you remember, guys, what is India's GDP? It's somewhere around $2 trillion. Okay, and if you talk about UK's GDP, okay, and that is also $2 trillion. If I ask you which country is richer of the two, if I ask you which country is richer of the two, can you tell me which country is richer of the two? Can you tell me which country has richer of the two? Is richer of the two? Which country is richer of the two? Can you tell me? Can you tell me? Can you tell me? See, both countries are more or less at the same level. But if you talk about people, then people of UK are more richer. Do you understand? People of UK are more richer. Okay, why is that? Because less number of people are making this high GDP, and over 1.3 billion people are making this GDP. Okay, now that is the same thing with internal energy as well, guys. That is the same thing as with internal energy as well. Population is really important. Just because you have more energy doesn't mean you have more energetic molecules. Okay, if this one has a lot of moles, let's say this has 100 moles of gas and this only has 1 mole of gas, then of course this one will have more energy, then of course that one will have more energy. But you also have to look at something else, guys. You also have to look at something else. You have to look at something called the average energy contained in every molecule. Okay, you have to look at the average energy contained in this molecule, and you have to compare that, the average energy of all the molecules, not the total energy. Do you understand what I'm saying? Do you understand what I'm saying? You have to compare the average energy, not the total energy. So here actually the answer is we can't say yet, guys. We can't say yet. We have to compare the average energy of all molecules, and this is where zeroth law of thermodynamics comes in. Okay, what exactly matters is what we zeroth law of thermodynamics will tell you. Okay, so what exactly, first of all, let's understand what is zeroth law of thermodynamics. Okay, what exactly is zeroth law of thermodynamics? Zeroth law of thermodynamics says that, yes, Afra, I will do that. Okay, zeroth law of thermodynamics says that, let's say I have three systems A, B, and C. Okay, I have three systems A, B, and C. Okay, and in this case, A and B are in equilibrium. A and B are in equilibrium. What that means is that they are not, overall their net heat exchange is zero. And also at the same time, B and C are in equilibrium. What that means is their net heat exchange is also zero. Then zeroth law of thermodynamics says that if A and B are in equilibrium, and if B and C are also in equilibrium, then A and C will be in equilibrium. Okay, then A and C will be in equilibrium. Okay, now why was this law created? First of all, you have to remember, as far as discovery is concerned, zeroth law of thermodynamics wasn't discovered first. The first law was discovered. But why was this law created? Okay, this law was added later because this tells us about something called a fundamental quantity that we added later because of this law, called temperature. This law talks about something which is very fundamental to all systems, called temperature. Okay, very fundamental to all the systems, called temperature. Here, in more energy doesn't mean more temperature. Okay, and here, if they are in equilibrium, what that essentially is saying is that temperature of A is equal to temperature of B, and temperature of B is equal to temperature of C. That means temperature of A will be same as temperature of C. Zeroth law of thermodynamics lets us define a very fundamental variable of a system called its temperature. It's there just so that we can define this fundamental quantity, because as we know, energy is not sufficient to tell us in which direction the heat flows. Energy is not sufficient to tell us in which direction the heat will flow. Okay, whether it will flow from left to right or right to left. Okay, what is sufficient though? What is sufficient? Temperature. Temperature tells us where the heat will flow. Okay, that's why, yeah, Sakshi is correct. Okay, the zeroth law was created after all the other laws were created. First came the first law, second law, third law, and then afterwards they're like, we need extra laws, so they created zeroth law. Okay, just to define what? Just to define temperature. And temperature is defined in general. What temperature tells you? Temperature tells you basically the average energy of all the molecules. Temperature tells you the average energy of all the molecules. Okay, So that is why we have zeroth law of thermodynamics. My statement, if you do not like, they have also given statement. It states that if two thermodynamic systems are in equilibrium with each other, with the third one, then they are also in equilibrium with each other. Okay, two thermodynamic systems are in equilibrium with a third one, then they are also in equilibrium with each other. Okay, that is zeroth law of thermodynamics. I hope everybody is following so far. Okay, now if you understand so far, other than this, there is no use of zeroth law of thermodynamics. Okay, other than this, there is no use of zeroth law of thermodynamics. So that's it. Let's talk about the next thing called concept of internal energy. Okay, now, once again, you guys know that if I have a container of gas and the molecules inside this container will keep on moving around in all directions, and when they are moving around in all directions, these molecules will have kinetic energy and these molecules will also have potential energy. Okay, now if you are talking about ideal gas, if you are talking about ideal gas, then for ideal gas molecules, there will only be kinetic energy, there will be no potential energy. Okay, why am I saying that for ideal gas potential energy is zero? Because for ideal gas, guys, for ideal gas, there is no force of attraction or repulsion between the molecules, and for potential energy you always need such forces. Okay, potential energy can only be defined in presence of such forces. For ideal gases there are no forces, so for ideal gas there is only kinetic energy, there is no potential energy. The sum of that entire energy is called the internal energy. The sum of that entire energy is called internal energy. And now, guys, as far as ideal gas is concerned, as far as one second, let me remove this. As far as ideal gas is concerned, oh my god, you design ideas now. जान ले लेंगे भाई. As far as ideal gas is concerned, we know the internal energy. Okay, as far as ideal gas is concerned, we know the internal energy because we studied something called the kinetic theory of gases. That was the last chapter, guys. And in kinetic theory of gases, we studied something called law of equipartition of energy. Okay, law of equipartition of energy. Okay, what does law of equipartition of energy says? Law of equipartition of energy says that if I have a container and inside this container there are a lot of gas molecules, then in that case each molecule will have a certain energy, energy, energy. Okay, and what kinetic theory of gases said that the average energy, okay, of one molecule, the average energy of one molecule is F by 2 into kb into T. Okay, what is F here? What is F here? What is F here? The F is called degree of freedom. Kb is um Boltzmann constant, okay, R divided by N. Okay, and similarly, if it has n number of molecules, okay, if it has n number of molecules and it has n number of moles, okay, and number of moles, then this overall energy we calculated the formula as F by 2 into N into R into T. Do you guys remember? Do you guys remember? I hope you guys remember. Yes, I hope you guys remember. Okay, so this was the total energy of the system. By the way, total energy of the system can also be written as N into F by 2 kBT, okay, which we derived as this, which we later did some more changes into it, and we derived it as this. Okay, but yeah, the total internal energy is given by this. I hope everybody understood. Okay, so now let's talk about internal energy. Okay, let's talk about internal energy. ये इधर थोड़ा गलत लिखा है थोड़ा सा. Let me just remove this. Okay, let me just remove this because जो गलत है वो तो गलत है ना. गलत है वो तो गलत है. We will not talk about गलत है क्या. गलत है वो है. Okay, yeah, let's talk about this. Okay, the internal energy is a state function and it doesn't depend on its path. Let's even remove this. Okay, let's remove this as well. Okay, so What exactly is this? Now, internal energy, guys, you have to understand is defined for all different points. If I ask you what is the internal energy of this gas, what is the internal energy of this gas at point 1, then the internal energy of this gas at point 1 will actually be equal to F by 2 into N into R into T1. Okay, where T1 is the temperature of this gas at point 1. Similarly, if I ask you the internal energy of the gas at point 2, it will be F by 2 into N into R into T2. Okay, I hope everybody understood. I hope everybody understood. Now, if the gas comes from 1 to 2, if the gas comes from 1 to 2, it has many different paths that it can follow. And when it does, we get something called change in internal energy. We get something called change in internal energy. And what will be the change in internal energy? By the way, it's written as delta U, and it's basically the final internal energy minus the initial internal. Final internal energy minus the initial internal energy. And if you see, it will just be equal to F by 2N into R into T2 minus T1. Now, this, guys, is a state function. Do you guys remember we defined something called a state function? I talked about state function somewhere. Where is it? Where is it? One second. Huh? Where is state function? Where is state function? State, static, dynamic, you guys, state functions. I defined something as state function and talked about change in internal energy is same for all of them. That is true here as well. That is true for internal energy, because internal energy, if you come along path A or B or C, it doesn't matter which path you follow, the change in internal energy will always be U2 minus U1. U2 minus U1. Change in internal energy will always be U2 minus U1. It will be same for all paths. It will be same for all paths. It's kind of like displacement. It's kind of like displacement. I hope everybody understood. Really hope everybody understood. Okay, that's why it's a state function. It's a state function. Okay, I hope everybody understood. Really hope everybody understood. Okay, now guys, before doing the next thing, let's talk for 2 minutes about Vedantu's Pro platform and what we have for repeater batches. Okay, if you're a dropper or a repeater, guys, then Vedantu's Pro platform has a very good opportunity for you. We have on our platform now the top faculties from Allen Chandigarh. Okay, these people were teaching at Allen Chandigarh. These are India's top faculties. Okay, they have taught all the best students before, and they are now on Vedantu platform to teach you guys. If you want to study from them and take a 6 month course and complete your entire syllabus within that 6 months, you need to go to vdnt.in/ytpro. Yes, where is it? Where is it? God, yeah. Vedantu Pro, yeah, the subscription link is available in the description first of all, but you need to go there and use my coupon code to get the discount. Okay, and by the way, the discount is 20%, but okay, whatever, you have to remember the batches are starting from 21st September. That is yesterday if you want to join. Okay, that is yesterday if you want to join just for JEE droppers. It's a good batch with the top faculty members. Okay. Anyways, guys, now let's talk about one last question. I'm going to give this question as homework. Okay, I'm going to give this question as homework. Please write the answer in comments. Please write the answer in comments and tell me what the rule is. Okay, yeah, very good, very good, very good. Yeah, all of you are the toppers. Either you are toppers already or you are going to be toppers in the future. Okay, there are only two possible states. Okay, any other states? I don't think anybody like that is here. Okay, so answer me this question in the comments. Also at the same time, guys, if you haven't joined our Momentum with Vedantu Telegram group, please join our Telegram group, and you get the notes and the quizzes and everything there. Okay, notes and assignments and quizzes, everything there. Alright, guys. So that's it for today. That's it. Balram saying I will give more questions for homework very soon. Do not worry. Okay. That's it for today, guys. I will see you again very, very soon. Okay. Have a nice day. Have a nice day, everybody. Thank you so much for being here. And I will see you again tomorrow. And bye bye. Bye bye.